So we've been doing the first derivative test to find local extreme values. The nice thing about that being it can always be used, it always works. The negative is it is time consuming. It takes time. So there is a faster test that we can use to find local extrema, and that's the second derivative test. And what we're looking at is we want to see where is the first derivative 0. In other words, we have to have a horizontal tangent, and it must be a horizontal tangent. And so if I had something that has a horizontal tangent here, and then if the second derivative is negative, meaning it is concave down, then there would be a relative max here. If I have a horizontal tangent and it's concave up, I would have a relative minimum. This is nice because it is a pretty quick test to do. However, there's a limitation. We cannot use this test if the second derivative is 0 at that point or undefined. The undefined is a bigger issue because it's typically undefined when the first derivative is undefined. So if there are corners or cusps or discontinuities or vertical tangents, we can't use the second derivative test on those points. And we're forced to use the first derivative test then. So an example of how this is used, let's say I want to find the extrema for x cubed minus 12x minus 5. I could do the first derivative test, which would require taking my first derivative, however, I don't have to. Polynomials especially are really nice to find extrema for using second derivative test because of the fact I don't have to worry about differentiability and having places that are not differentiable. So I'm going to use the second derivative test, which means I just need to know where is f prime equal to 0 so that I can find those horizontal tangents. And this is at x is 2 or x is negative 2. And then I need to find the concavity at these 2 points, which means I need my second derivative, which would be 6x. So my second derivative at 2 is 12, so it's concave up. My second derivative at negative 2 is negative 12, so it's concave down. So what this means is because at positive 2, because I have a horizontal tangent and it's concave up, there is a relative min. And then at x equals negative 2, because there's a horizontal tangent and it's concave down, there is a relative max. And if I wanted to find exactly what those were, I would then plug in 2 and negative 2 into here so to find out the actual min and max values. But this is just to show how quick the second derivative test can be compared to the first derivative test. Just remember the limitation on the second derivative test, though.